I'm Yuu Igarashi from Kyoto University. Today, I'd like to present our research on polymorphic gradual typing. We studied other aspects of integrating polymorphic types and dynamic types. Okay, first of all, gradual typing aims at smooth integration of static typing and dynamic typing. So here's a gradually typed version of add function. Here, star expresses a dynamically typed part or omission of type annotation. So here, the type annotation for the second parameter is omitted. Then, if programmers supply a wrong argument for the first parameter, they can enjoy static typing because there is a type annotation. On the other hand, they provide a wrong argument for the second parameter, they can enjoy dynamic typing. And gradual typing brings us such a flexible typing. Okay, let's look at the gradual typing from high level. In the simply typed case, we have two languages. One is the source language, gradually typed random characters, abbreviated by GTLC, and another is the target language, rem characters, which is one of the CAS characters. So first, GTLC type checks terms, and here you should note that star always passes type check. So the two examples are well typed in this case. Then terms are translated to rem characters by inserting a cast to perform dynamic type check. So the first example gets a cast from star to int, and the cast from bool to star is inserted to the second example. And finally, terms are executed in rem characters. Okay, the second example is reduced as follows. First, the two arguments are substituted, and here bool is not equal to int, so it raises rem, runtime error. Okay, this is the standard framework of polymorphic, this is the standard framework of simply typed gradual typing. Okay, our goal is polymorphic gradual typing. It aims at smooth integration of polymorphically typed terms and dynamically typed terms. So the most motivating examples are the displayed ones. In the first case, a dynamically typed function is passed to the polymorphically typed context, and the second example is the opposite. Our language enables such flexible integration. So, as you know, there's some research on polymorphic gradual typing. Polymorphic rem characters has been studied by Ahmed et al. Its main feature is name generation or runtime type generation to ensure parametricity. The language corresponds to the target characters in the framework. However, there is no research on the whole framework of polymorphic gradual typing. So we completed the missing parts by developing the two languages. One is our source language, SystemFG, which is an extended version of GTLC. And another is the target language, SystemFC, which is an extended version of polymorphic rem characters. Then we proved almost all the desired criteria for polymorphic gradual typing. And we extended the polymorphic rem characters with the distinction of type variables. Okay, this is today's picture. So, I'd like to present two main topics today. First, we explain the desired criteria for polymorphic gradual typing. Especially the two non-trivial properties are explained. And second topic is the distinction of type variables. Okay, let's get into the details. First, the desired criteria for polymorphic gradual typing. And you should note that in this section, we mainly focus on the source language SystemFG, okay, the source language. Then, generally speaking, the desired criteria consist of the 5 properties. We should design our gradually typed language so that all the criteria are covered. Okay, in our case, we proved almost all the desired criteria except for the hardest property, the gradual guarantee. And especially the first and the last properties require non-trivial devices. So I'd like to explain these properties and the key ideas. Okay, first criterion is Conserve Duty over typing of system F. The property says a purely statically typed term is well typed in system F if and only if it is well typed in system FG. with this property, we can move a purely statically typed code between gradually typed version of the interpreter and the statically typed one with this in mind. So we have to design our type system so as to obtain this property. However, a gradual type system has a special feature which may break this property. That is type consistency. It is used to relax type check for function application in source language. In ordinary static typing, the parameter type T11 and the argument type T1 should be equal. But here, in gradual typing, it is enough that they are consistent. This is the source of flexible typing. So the relation is obtained from type equality by regarding star as a wildcard. And in polymorphic gradual typing, it decides how we can integrate polymorphic terms and dynamically typed terms. So the main part of designing polymorphic gradual typing is design of type consistency. Okay, so let's look at the naive type consistency about polymorphic types. You can also find similar definitions in the previous polymorphic blame calculus. And it is so simple that I have nothing to say, but it seems to work well because star can be consistent to type variables. So the example below said that the most motivating examples are covered by this naive definition. Is it okay? No. We have a problem. If we adopted the naive definition, we would encounter the counterexample of the Conserve Duty. Please look at this term. In this term, the parameter type and the argument type do not match, and this term contains no dynamic types. So this is an ill-typed system F term. However, this term would be well-typed in system FG due to the naive type consistency. Formally, this would break only if part of the conservativity. So this problem, So this problem is not covered in the previous research. So we fixed the type consistency to solve the problem. The idea is very simple. In the left rule, we can relate a polymorphic type and a non-polymorphic type only when the non-polymorphic side contains at least one star. Intuitively, relating a polymorphic type and a non-polymorphic type is specific to gradual typing, so there should be the feature of gradual typing, the dynamic type. Okay, and the right rule is added to restore reflexivity of polymorphic types. As a result, we proved conservativity over typing of system F. Okay, the second criterion is the gradual guarantee. Let's begin with what the gradual guarantee is. First, I'll give you informal explanation. Please consider the situation where you are using a gradually typed language and you prototype code omitting the type annotation. And you have found that the function works for the integer arguments. So you added type annotation int for more stable developments. Of course, you hope you will get the same result true. However, what if the result changes? You will be very, very confused. You will never use this programming language. Yeah. So fortunately, the gradual guarantee ensures that such a confusion never occurs. The gradual guarantee allows us to enjoy gradual typing without unexpected behavioral changes. So let's look at the formal statement. In this statement, the square subset means the left side is more precise than the right side. Okay, the first statement said that if a more precisely typed term converges, then the less precisely typed term also converges, then the results are in term precision again. Intuitively, making types less precise preserves behavior. Okay? And the second statement is about the opposite transition from dynamic to static. So such a transition means adding type annotations. So the second statement said that if the type annotations are correct, we get preserved behavior. Otherwise, if the type annotations are wrong, it results in type errors. Okay. more formally, we introduce two partial orders, type precision and term precision. The type precision consists of the three rules above. It is obtained from type consistency by removing symmetricity. And the key rule of term precision is one about lambda abstraction. Its type annotation can evolve in the sense of type precision. And the other rules of term precision are trivial congruence rules. Okay, we are ready for the main topic. We extend the discussion so far to polymorphism. However, we immediately encounter the counterexample of the first gradual guarantee. As convention, we define ascription as displayed first. And the two terms in the term precision is a counterexample of the gradual guarantee. We suppose a trivial congruence rule for the big lambda. And then the only differences are the type annotation of small x and the ascription of number 42. Then the left term is evaluated to 42 because there are no casts after cast insertion. Then the first gradual guarantee says making types less precise preserves behavior. So the right term should also be 42. However, that's not the case. To understand why, we have to explain how the target language system FC reduces type application. But you know it. But let me explain their name generation or runtime name generation in case you were sleeping. And our target language system FC performs name generation for type application. And name generation prevents non-parametric behavior of polymorphically typed terms. Okay, look at this term. This term would not behave parametrically because the behavior of these casts would depend on the applied types if we perform the type substitution. So the whole term should always raise brain. Let's look at what happens if we use name generation. Okay, when we construct type application, we generate a type name instead of type substitution. Then the generated type name is placed in the left side of this triangle. And vectordex is constructed. And here, we don't look through type names. That is, x is not equal to int here. So it raises brain, as we expected. As you know, it ensures parametricity in their setting. Okay, let's get back to the counterexample. We have to reduce the right term. After cast insertion and some evaluation, we get into this state because, as explained, type substitution did not occur, and 42 is int, and its ascription is star, and finally, the ascription of small x is larger x. You can trace them. And then it raises brain. However, these results breaks the first gradual guarantee because making types less precise changes behavior. So the essential problem is that we can change a type variable into star inside a big lambda. It seriously changes how type abstraction works. So we fix the term precision. We restrict term precision not to change how type abstraction works. Intuitively, we disallow type precision between type variable and the star inside big lambda and for all. As a result, we have excluded the last example. And in practice, such term precision means we have to change dynamic types into type variables at once when we evolve a dynamically typed function into big lambda. Otherwise, we may not enjoy the gradual guarantee. Okay, then now we have not proved the property, but we believe that the defix is enough. We conjecture the gradual guarantee for polymorphic gradual typing. Okay, the second topic is the distinction of type variables. In the target language system FC, we have two kinds of type variables. One is a static type variable, annotated with S in gamma and big lambda. It can be consistent to only itself. So the leftmost consistency relation holds, but the others do not. Another is gradual type variable, annotated with G and gamma and big lambda. It works in the same way as other base types such as int or bool, so it can be consistent to star. And the distinction is first observed in the other paper, but this is the first time to apply the distinction to the whole language design. So I'd like to explain one of the topics about application, reduction rules. In the target language system FC, we have two reduction rules for type application corresponding to the distinction. For static type variable, we substitute A into X in the same way as the usual system F. On the other hand, for gradual type variable, we generate a type name in the same way as polymorphic blame calculus. This fine-grained handling of type application brings us two merits. First, it makes very clear that how system F terms can be embedded to our calculus. We can consider the type abstraction of system F uses a static type variable. And second, the distinction enables ordinary type erasure for static type abstraction. We implemented a type erasing interpreter on the basis of this fact. The interpreter is verified as an artifact. Please try it if you have interest. And then, moreover, we apply the distinction to the term precision relation or type precision or type consistency, but we don't look at them. Please check out our paper for more details. Okay, here, we summarize the main related work here. But we don't take a close look at them because of time constraints. These papers will help you learn more details. Okay. I'd like to summarize today's presentation. We developed the whole framework of polymorphic gradual typing. And we developed two languages. And one is the source language, systemfc, and another is the target language, systemfc. And we proved almost all the desired criteria for polymorphic gradual typing. And finally, we explained our novel application of the distinction of type variables. Okay. In future, we will prove the gradual guarantee first. And it is also interesting to prove parametricity of system FC adapting Ahmed-Tutor's logical relation. And finally, we will formalize our implementation of the interpreter on the basis of cryptographic lambda calculus. Okay, that's all. Thank you for listening.